Hello, and welcome back. We are still working through our introductory unit for differential equations, and I apologize for my voice today. I'm fighting a cold, but hey, we can still do calculus. So our learning objective today is to introduce and learn to solve a special kind of differential equation, growth and decay. In many applications, the rate of change of a variable y is proportional to the value of y. And if y is a function of time, the proportion can be written as follows. dy dt equals ky. So the rate is proportional to the value of y, and that k, that's a constant, and we call it the proportionality constant, which we'll talk about in a little bit. And this differential equation has a general solution of y equals ce to the kt. So first of all, before we move on, let's verify that y equals ce to the kt is in fact the general solution of the differential equation dy dt equals ky. So first off, we need to start with our separation of variables. So we're going to get all the t stuff and the constant on the right and all the y stuff on the left. And then we can take the antiderivative of both sides. So we get the natural log of y equals kt plus c. And in order to get y out of there, we need to exponentiate both sides. So we get y equals e to the kt plus c. Now notice that c is up here in the exponent. So I could actually rewrite that as e to the kt times e to the c, and e to the c is still a constant. So I'm going to rewrite that one more time as y equals that constant times e to the kt. So there is our verification. Now you're going to need this equation a lot, so learn to love it, memorize it. What we just talked about was called the exponential growth and decay model. And it says that if y is a differentiable function of t such that y is greater than 0 and y prime equals ky for some constant k, then y equals ce to the kt. Where c is the initial value of y, that's going to come in handy, and k is the proportionality constant. Exponential growth occurs when our constant, our proportionality constant, is greater than 0, and exponential decay occurs when k is less than 0. So this example says the rate of change of y is proportional to y. When t equals 0, y equals 3, and when t equals 2, y equals 6. So what's the value of y when t equals 3? Okay, oh, there's a lot going on there. First of all, when you read it, the first thing you see is the rate of change of y is proportional to y. So that's code for this right here. The rate of change is proportional to y. So we know that we're working with our exponential growth and decay model, which is y equals ce to the kt. So we're going to need to solve for c and for k. And if we're solving for two variables, thankfully, we have two sets of inputs. So we'll use the initial value. We'll plug in 3 for y and 0 for t. And e to the 0 is 1. So we know that c equals 3. And that makes sense because c is known as the initial value. So I actually could have just taken c from right up here to begin with because I have an initial value at t equals 0 of 3. So anyway, but it works out even if you have to find c. And then we'll use our next value to find k. So we know c, so right now we have y equals 3, e to the kt, let's solve for k. So we'll plug in 6 for y and 2 for t. Divide both sides by 3 and take the natural log of both sides and divide by 2. So our proportionality constant is 1/2 ln2. So now we have a full-on model of this. Y equals 3e to the 1/2 ln2 times t. And now if we want to know the value when t equals 3, now let's clean this up. We can just plug in 3 right here for t, put it into your calculator, and you get about 8.48595. Here you can see the graph of it, and we got it right. Next one, a company's annual revenues drop, from $530,000 in 2018 to $386,000 in 2020. That's a bummer. If the revenue is following an exponential pattern of decline, what is the expected revenue in 2023? So we have an exponential pattern of decline, which means we can use this model, y equals CE to the KT, and we have an initial value that they told us. Our starting time is 2018. Our initial value is $530,000, so I've plugged that right in here for C. Now we can find K by plugging in our second point, which is 2. So this is 2 years later. 2 years later in 2020, the revenues were $386,000. So you'll notice I just dropped off the last 3 zeros here just to make it simpler. So 386 equals 530e to the 2k. And then we can solve for k. We get about negative 1.5852. So now we can create a general model. And if we're looking for the revenues when t equals 5, we can just plug 5 into our general model there for t. And it looks like the revenues will be down to about $240,000. So I think they might need to change their business models, huh? During a certain epidemic, maybe the one that affected that previous business, the number of people that are infected at any time increases at a rate proportional to the number of people that are infected at that time. If 1,000 people are infected when the epidemic is first discovered and 1,200 are infected 7 days later, how many people are infected 12 days after the epidemic is first discovered? We have a rate proportional to the number of people, so we know we can use our exponential growth model. We also have an initial condition of 1,000. So we're going to start with 1,000 e to the kt. Now we can solve for k by plugging in our second point. So 1,200 equals 1,000 e to the k times 7. This is 7 years later. 1,200 people are infected. And now we can solve for k. So k is natural log of 1.2 over 7. Using that then in our general model, we just have to plug in 12 for t. So it looks like 12 days later, we'll have about 1,367 people infected. Okay, now let's talk about insects. Suppose a population of insects increases according to the law of exponential growth. There are 130 insects after the 3rd day of the experiment and 380 after the 7th day. So approximately how many insects were in the initial population? The initial population is now the unknown. So we're still using our exponential growth model. However, we need to solve for both C and K this time. So we'll just plug in 0.1 and we can start finding C. So at 3 days, there was 130 insects. So we'll get 130 equals CE to the 3K. All right, so we'll solve for C, and it's going to be in terms of K still, but that's okay. That's all right, no big deal. Hold on to that for a second, and let's plug in point 2 using that C. So after the 7th day, there were 380 insects. So now we've got 380 insects. Here's the C that we got from up here, and then 7 days later. Now we have just one variable, and we can solve for K. So I divided both sides by 130. Let's clean this up. And then combined these two e's to be e to the 4k. So k is about 0.282. Now we can plug that back in to figure out actually what c is. So c equals 130 times e to the -3 times our k. And so it's about 58 insects initially. Okay, extreme heat applied to a colony of microorganisms causes the size P, so I think that's population, the size P of the colony, measured in grams, to decrease according to exponential decay, and it's decreasing at -0.4p, where T is measured in hours. The size Q of a second colony of microorganisms, also measured in grams, decreases at a constant rate. Oh, that's different. A constant rate of 1 gram per hour, according to a linear model. Okay, so we've got dq dt equals -1. If at time t equals 0, the first colony has a size of 2, and the second colony at time t equals 0 has a size of 3, at what time will both colonies have the same size? That's a lot going on. Let's start with the first colony, and that was the one that was with the exponential decay, and we do have an initial value of 2, and we have our k value of -0.4. So there's our model for the first one. Now, the second colony, that was a linear model. So that one, if it's got a rate of -1, that's a slope of -1. And we also have a point of 0.3. So we can put a line together. It's a linear model for that one. Y equals -1x plus 3. So here's -1. That's our slope. So now let's go back and see if we can answer the question. At what time will both colonies have the same size? Oh, okay, so that's when the populations are equal, so we'll set them equal to each other. And to do this on a calculator, I find that it's just really easy to set it equal to 0. So subtract this to the other side, and then graph that, trace the zeros, and it looks like about 2.156 hours. The microorganisms will have an equal population. Fun stuff. All right, so that is exponential growth and decay. We'll see you next time for logarithmic growth and another fun thing that has to do with hot chocolate. Talk to you later.